Hello friends, and welcome to another sleepy science journey. Before we drift deeper, pause with me for one soft heartbeat of calm. If you enjoy soft science at night, please like, share this moment, and subscribe to catch the next wander. Tonight we step into the frame that nothing can slip outside. There is no beyond to it. Every glance, pulse, and footprint needs its address in meters and seconds. Light cannot outrun its limit, and clocks negotiate their truth inside its rules. Feel that certainty gather at the edges of thought, then let the first idea arrive. Space-time is the quiet structure that holds every moment in place. It is not a stage beneath events. It is the event and the stage together. One continuous arrangement of three distances and one duration. Coordinates are how we point to an occurrence. A meter and a second are how we measure change within that arrangement. Physics uses this union because separate space and separate time cannot keep measurements consistent for different observers. When objects move quickly, their intervals of distance and duration adjust so that the laws remain the same for everyone. This adjustment is not a trick. It's the pattern reality follows, expressed softly as relationships rather than absolutes. Gravity follows from that pattern in the fabric. Massive bodies bend the structure, and free objects take the straightest paths available within the curve. Those paths are called geodesics. A planet orbiting a star is not pulled by an invisible thread. It is traveling through a shaped environment that guides motion without a hand. Light follows the same rule. Its path arcs near mass because the structure itself is not flat there. Even clocks pay attention to shape. They slow in deeper gravitational wells and speed up in lighter ones, keeping faith with the geometry that hosts them. The universe uses these rules everywhere. Starlight bends around the Sunday. Atomic clocks tick at slightly different rates on mountains and in valleys. Lasers confirm that the speed of light in vacuum holds steady no matter how you move. Navigational satellites mark their days with relativistic corrections, so your phone can place you on a map. Telescopes find distant galaxies stretched and magnified by matter you cannot see directly. Detectors listen for passing waves in the structure when compact stars collide far away. You do not need to solve equations to rest within this picture. It is enough to know that motion, distance, and time belong to one fabric. When you breathe slowly, your heart measures seconds within that same composition. When you close your eyes, the room's quiet reminds you that stability can be gentle. Knowledge does not have to be loud to be certain. Let a calm thought settle. The universe stays coherent because its foundation is consistent, and you are carried by that consistency tonight. If sleep wants to arrive, welcome it like a familiar friend stepping through a doorway, and allow the steady rhythm of space-time to hold the edges of your dreams. We call it four-dimensional because a place is never complete without its moment. A hill is only a hill when we include the instant you stood upon it. In physics, an event is that marriage of position and time, a single dot in a larger arrangement that holds every dot together. The arrangement is smooth enough for curves to be drawn and compared. Mathematicians call it a continuum. Engineers rely on it without remark. The value of this picture is steadiness. Different observers may label the axes in different ways, but there is a single measure between events that does not change. That invariant distance through space-time is the anchor that keeps comparisons honest, so a cause always precedes its effect, and no signal outruns light's limit. The architecture that governs these measures is written into something quiet and exact. It tells rulers how to stretch, and clocks how to count along any chosen path. In empty stretches far from mass and radiation, the instructions reduce to the simplest form. and straight lines remain straight when tested with light pulses and synchronized clocks. Near dense regions, the same instructions bend the map. You do not feel a mysterious hand. You trace the shape of the ground itself. Spacecraft use this rule in practice. Mission planners do not beg the void to cooperate. They solve for a route the craft can coast along, and the craft arrives at a world millions of kilometers away because the calculation matched the geometry, not because of a hidden pull through nothing. This union of space and time replaces older absolutes with a relationship that protects physical law from perspective. Electricity and magnetism keep the same equations, whether an experiment sits still or glides smoothly along. To make that possible, moving rulers shorten in the direction of travel, and moving clocks tick more slowly when compared to those at rest. The change is not a flaw in devices. It is the environment insisting that all observers describe light with the same speed. When that speed stands firm, the rest of the world adjusts to preserve consistency. The comfort of this idea is that it does not pick favorites. No vantage point is exalted. You can choose coordinates that make your work easy, but nature has already chosen the quantities that will remain the same for everyone. The squared interval between two events, computed with the fabric's signature and balance, will match across frames. That shared value binds the stories told by different observers into one narrative. Disagreements about lengths and durations become translations, not contradictions. Where two people once argued about whose clock was right, they now compare notes about the same invariant line. Astronomers see the usefulness of this language in simple ways. Light from distant sources arrives stretched when the space it crossed has grown while the beam was in flight. The shift is not an extra paint on the beam. It is a record of the distance scale changing while the signal moved through it. The background glow from the early universe presents a spectrum that fits a cooled remnant of a hotter time. Its uniformity across the sky fits a geometry that smoothed differences before atoms could even form. In laboratories, beams of fast particles live longer when observed from the outside frame, because time along their paths does not match time along ours. None of this requires a privileged seat. It simply requires respect for the structure that every experiment shares. You can picture it without equations by thinking of music written on a staff. A note has a vertical place that sets its pitch, and a horizontal place that sets its moment. Remove either, and the tune breaks. Keep both, and you can hum along, bar after bar, without confusion. Space-time carries reality in the same way. Where and when define the melody of events, and the distance measured within that staff remains faithful, even when the page is tilted. The world's fairness rests on that faithfulness. Alarms ring on time in airplanes. Signals sent to a probe reach it when expected. Radios synchronize with transmitters a continent away because the framework does not play favorites, even while it adjusts lengths and ticks to protect deeper rules. The kindness in this picture is more than technical. It says that difference need not be disorder. Two observers moving gently past each other can disagree about a span of street or a stretch of seconds, and still agree about the connection between two sparks. Causality survives because the fabric's design protects it. Light cones carve the possible from the impossible around every event, drawing a future that can be touched and a region forever outside touch. The shape of those cones does not depend on your choice of axes. It is built into the structure, the same for all, the same everywhere. When maps bend near mass, we do not accuse the traveler of wandering. We thank the map for telling the truth. A satellite that falls freely toward Earth is not disobeying Newton and obeying something new. It is following the straightest available track in a curved neighborhood, and the ground interrupts that track with a firm surface. The weight you feel is the surface pressing you off your natural line. Stand on a scale and watch the needle hold. Step into an elevator that releases its cables and feel the weight vanish while you float. Nothing about you changed. The path changed. The scale's springs relaxed because the floor no longer forced you away from your preferred curve. In the same spirit, consider how planning a mission depends on the metrics details. Engineers choose injection speeds and angles so that a spacecraft proceeds along a path requiring minimal course correction. Midway checks correct tiny drifts from models, not because space is fickle, but because small pressures from sunlight or vapor leaks at joints push the craft gently off the designed line. The big picture remains stable. The craft arrives on schedule because the background structure is patient and predictable. The satisfaction of such arrivals is not merely technical pride. It is a human relief that our measurements meet a world organized enough to welcome them. 9. The precision grows finer when you think about how to compare clocks. To claim that 2 ticks match, you must agree on how to bring the clocks together or how to exchange signals between them in a way that honors the geometry. The procedure is not arbitrary. It is forced by the requirement that light's speed remain constant. When 2 observers use that procedure, their results can be compared. When they do not, their disagreements are noise. The geometry forgives honest differences in motion by giving both observers the same invariant to hold, and it refuses sloppy comparisons by making them obviously frame-bound. On a quiet night, these claims sound almost like manners. Keep your measure fair. Respect the path the signal took. Compare like with like. The reward is clarity across motion and distance. A lab bench near the window and a radio dish in the desert both submit to the same rules and earn the same right to certainty. That is why a deep space photograph with pinprick stars can be interpreted a decade later with better models and still fit. The staff did not change. We only learned to read another harmony written there all along. A single soft image may help you drift while it lingers. Imagine a page of slow, even handwriting where each letter knows its place in the line, and each line sits at a patient distance from the next. You can tilt the page, hold it close, or read it across the room. The words do not scramble. The meaning stays. SpaceTime offers that same calm to everything that moves or rests within it. The 4-dimensional weave is simply the promise that your portion of the story connects gracefully to every other portion, and that the distance between 2 moments can be trusted even when viewpoints differ. If that steadiness eases your breath, let it. If it loosens your hands, let them settle. The room will hold. The structure beneath all change will remain, and your place upon it, here and now, is enough. Light in vacuum keeps one speed for every observer who measures carefully. Laboratories have rushed detectors along tracks and rotated delicate interferometers through every quarter. The number does not budge. When the world refuses to change that value, it forces a gentle trade elsewhere. Distances along the direction of motion compress for moving rulers used by an outside watcher. Durations between ticks lengthen for moving clocks when compared side by side later. The exchange keeps the equations of electricity and magnetism identical for all, so a wave that carries both fields does not need to ask who watches it to decide how to behave. This constancy has a consequence that feels odd until it becomes familiar. 2 flashes that look simultaneous to one traveler appear staggered to another who glides by. The travelers are not mistaken. They slice the same block of space-time along different angles, and the order of distant events changes with that angle. What refuses to change is the order of events that can affect each other. Inside a light cone, a cause can reach its consequence. Outside that cone, no message can connect them. The boundary is not a suggestion. It is the boundary written into the fabric, keeping stories consistent across the universe. Old experiments taught this lesson with stubborn clarity. Devices that mixed light beams along two paths and brought them back together were expected, by some, to reveal a breeze through the ether if the Earth moved through a preferred medium. No such breeze appeared. Rotating the apparatus did not matter. The interference pattern stayed put. The result was not simply a null, it was a guide. Stop searching for a favored wind and accept that the speed of light is the same in all directions for any steady observer. From that acceptance, everything else follows cleanly, including how clocks and rulers must cooperate to keep the laws unchanged. Aircraft carrying precision clocks offered another check. Identical devices that counted time using steady atomic transitions were flown while their partners remained on the ground. After the flights, the tallies differed by tiny amounts, exactly in the sense needed to reconcile motion and height with the shared design of SpaceTime. The differences were small because the speeds were small compared to light, but small is not zero. Engineers who build systems that depend on synchronized signals do not shrug at small differences. They write them into the designs, so timing can be trusted across long distances. Particles racing through accelerators deliver similar evidence. Beams guided by magnets approach light speed, and their internal processes slow when seen from outside. The effect is not a mechanical strain. The particles feel nothing unusual in their own frames. It is the comparison that shows the change. Detectors count decay products that arrive later than they would if time were absolute. The counting fits equations that protect light's pace and reshuffle our expectations for length and duration to compensate. What protects you, as a listener in the dark, is the simplicity under the strangeness. The world chooses a single speed for its fastest messenger and lets geometry absorb the burden of fairness. That choice prevents paradoxes that would unravel understanding. Signals cannot arrive before they are sent. Two events outside each other's cones cannot trade influence, no matter how clever the device you imagine. The relief is that no hidden channel lurks to embarrass measurement. Causality is safe because the structure guards it with a limit woven into every map. To feel this without pictures, think of a steady drum at a distant parade. No matter where you stand along the street or how gently you walk beside the marchers, the beat reaches you with the same pace. If you begin to stroll, your stride and your sense of the intervals will shift against the storefronts and shadows you pass. But the rhythm itself does not ask your speed before it travels. Light's constancy is that rhythm. Your motion sets your relation to landmarks, not the beat itself. Consider also how this consistency helps in daily tools that never mention relativity in their user guides. Fiber networks time their pulses across continents. Radio beacons synchronize arrays of telescopes, so widely separated dishes behave like one. Scanners in hospitals count precise delays as signals cross tiny distances inside tissue. None of these would work cleanly if different labs had to guess at light's pace each morning. The shared value lets different rooms and different cities trust each other's timing with a confidence that improves health, navigation, and the quiet choreography of modern life. As the tide shifts from thought to rest, one more example can settle the mind. Imagine two observers watching distant lightning strike two hills. One rides a smooth train, one stands on the platform. To the rider, the flash closer to the train's nose arrives first. To the watcher on the platform, the flashes arrive together. Both statements are true within their procedures for comparing times and places. Neither opinion travels backward to cause a contradiction. The cone around each flash keeps influence pointed forward. Language adapts to describe the difference. The world does not fracture to accommodate it. There is tenderness in how the rules make room for many views without letting meaning slip. Physics does not demand that you abandon your experience of time's flow. It asks only that you accept a deeper accounting when events are compared across distance and motion. The accounting keeps everyone's stories compatible, and it does so by holding light's pace as the reference that never yields. Trust grows in that firmness. Engineers trust it when designing instruments. Pilots trust it when their radios speak. Astronomers trust it when their detectors time photons from objects that died before Earth formed. You can trust it too, not as a burden of knowledge, but as a quiet assurance that the world beneath your breath is lawful and kind. If a single metaphor can bridge you gently toward sleep, picture a river with a current that never varies. Boats of different widths and paddlers of different strengths must angle differently to reach the same opposite bank. But the water's speed is not negotiated, it is accepted, and paths are planned around it. Light's constancy is that water. Observers are the boats. The fabric's tilt is the angle chosen to keep the landing honest. Once that is understood, effort eases. You do not fight the current. You align with it, and the crossing becomes simple, steady, and sure. Gravity is not a thread tugging across emptiness. It is the shape of the map itself. When energy and momentum gather, space-time bends, and freely moving bodies trace the straightest lines available within that bend. Those lines are geodesics. A planet loops its star because the ground beneath motion is curved, not because an invisible hand pulls at distance. Stand on the surface, and you feel weight only where the floor prevents your own path from sinking toward the center. The push from below is the sensation of being held off your natural route. Suspend that push, and the feeling vanishes, not because gravity left, but because you were allowed to follow the line the map prefers. The equation that links matter to curvature is exacting and quiet. It balances what fills a region against how distances and durations fit together there. Far from heavy objects, the fit is nearly flat. Light rays travel as if the grid was straight. Near dense places, angles shift and lengths tilt, and paths that once ran parallel drift together or apart. None of this requires a medium. It requires only a rule that ties content to contour so motion can be read like a line on a relief map. Evidence for this picture arrived early and keeps accumulating. During a total solar eclipse in the last century, observers compared the positions of background stars with measurements taken when the sun was elsewhere. The starlight passed close to the solar limb and arrived slightly deflected, just as the curved map predicts. Later, radio waves skimming that same limb echoed back with extra delay because the route lengthened and time itself ran a touch slower in the deeper well. Spacecraft signals that pass near massive bodies include that delay in their budgets. The pulses reach home when schedules honor the bend. Closer to home, tides follow from curvature differences across our planet. Water bulges along the line connecting Earth and the Moon and recedes at right angles, not because the ocean is drawn away locally, but because neighboring paths diverge slightly as the map changes over a planetary radius. Solid ground flexes a little under the same rule. The effect is gentle here, yet in systems where the curve grows tight around compact stars, the stretching can tear orbiting companions apart and feed luminous rings of debris. In strong fields, additional signatures appear. Orbits precess when the nearest approach shifts a little each cycle. Perihelion points creep forward. Light can wrap partway around a compact mass before leaving, forming rings and arcs where multiple routes reach an observer together. Near the threshold where escape fails, trajectories spiral inward as if a funnel's lip had sharpened into a throat. None of this invokes new forces. It is the same law in a more emphatic landscape. revealing details that remain hidden when the map is nearly flat. Navigation uses the curved map as a working document. Deep space missions plan transfers that spend long stretches in free fall, letting the path do the work. Gravity assists borrow momentum from planets by sweeping past them along carefully chosen lines, changing speed and direction without burning much fuel. The savings come from cooperating with the terrain, not from gambling against it. Small course tweaks nudge the craft back onto the calculated geodesic when sunlight or outgassing nudges it aside. Arrivals match windows because the route was drawn on the right kind of map. Geodesy on Earth reads the same book at smaller scales. Laser pulses bounced from satellites map subtle variations in the field that reflect mountain ranges, ocean trenches, and the underlying flow of mass. Clocks, synchronized across laboratories, track how the rate of time shifts with elevation and density, letting researchers infer contours without digging. Railways, tunnels, and dams all benefit from a precise account of how the planet's shape and pull cooperate to guide water and stone. What seems abstract is a ledger of practical lines written into the world's body. The language of curvature also clarifies why weight vanishes in orbit. A crew circling Earth in a sealed cabin feels floor and ceiling lose meaning because the entire vessel follows a shared free-fall line. The astronauts are not beyond gravity, they are inside it, obeying geometry so perfectly that only the cabin's walls interrupt motion. A brief firing of thrusters tilts the world line, and every object aboard agrees at once. When the burn ends, quiet returns, and the straightest path resumes, a compromise reached without a vote. On larger canvases, the same principles guide lenses made of mass rather than glass. A galaxy cluster bends the routes of rays coming from sources behind it. Sometimes a single galaxy is sliced into several images. Sometimes a ring forms where the geometry is symmetric enough for many paths to arrive with equal delay. Astronomers read those distortions backward to weigh the cluster, counting matter that does not shine. Maps, drawn from bending, reveal structures that would be invisible. Otherwise, a fair census, built from light's compliance with the curved map. Curvature has a local meaning that protects simplicity. In a small enough cabin falling freely, the rules look like those of uncurved space and time. Test masses released together float side by side for a moment, as if gravity had vanished. Stretch the region wider, and a difference appears. Two nearby tracks that began parallel start to approach or separate, because the field is not exactly the same across space. That relative acceleration is the tidal signature, written by an operator that compares how neighboring geodesics change. You can test it with springs and markers, and you can compute it with the tools of geometry without invoking a force that pulls through distance. This is why a theory built on geometry naturally recovers familiar gravity, where fields are weak and speeds are small. The curved script reduces to an equation where attraction falls off with distance in a way long known to sailors, builders, and astronomers. Planets keep schedules that match almanacs. Falling stones land where arcs predict. Only when precision rises or masses grow fierce do the subtler notes show, nudging perihelia forward, delaying echoes, and bending rays. Even clocks that serve navigation pay respect at this level. Radio beacons cling to calculated orbits and broadcast phase patterns that receivers compare quietly. The equations that steer those broadcasts include small terms from curvature, so the phase remains faithful across oceans. When a surveyor stows a rover at night, it wakes to a sky full of signals already synchronized to a geometry that has not shifted while it slept. The peace of that stability is not accidental. It is engineered upon rules that large and small experiments have converged on with patience. the same understanding guides weighing the universe. When a background quasar is split into several images by a foreground mass, the arrival times of its flickers differ by hours or days, because each route through the landscape has a distinct length and rate. Measuring those delays lets astronomers infer distances and the overall scaling of expansion, cross-checking other methods with independent handles. It is a quiet practice. Watch, time, compare, infer. The spectacle of arcs and rings is beautiful, but the arithmetic behind them is careful and plain. Curvature also shapes soundless traffic within galaxies. Stars in a cluster share a potential well, and their motions trace the depth of that well in a way statistics can read. Gas settles into disks around compact objects, and heats as orbital energy turns into light while falling inward. Observers fit line profiles and brightness curves, with models built on the same geometry written at every scale. No single number explains a galaxy's dance. The map beneath it does, because that map is the very shape of space. Curvature maps turn motion into clarity and rest. Speed changes how much time a traveler carries between two meetings. The rule is simple to say and careful to apply. The closer a path approaches light's pace, the fewer seconds it gathers when compared with a gentler route. Each clock measures normally along its own line. The difference appears only when world lines are brought together and ticks are compared. That comparison reveals time dilation as a property of motion, not a fatigue in gears or atoms. It is space-time's arithmetic, counting steps along different routes and finding totals that depend on speed. A common story imagines twins. One remains at home. One rides a fast loop and returns. The traveler comes back younger by a small, exact amount because her path through space-time collected less proper time. The resolution is not a puzzle about who was really moving. It lies in the fact that the paths were not symmetric. The traveler had to turn, and turning changes the relation between frames. Draw both world lines, compute their lengths in the metric, and the difference falls out cleanly without drama. Experiments anchor this story at many scales. Particles produced in the upper atmosphere travel downward at high speed. In their own frames, they live the same brief lifetimes they always do. In ours, the span stretches, so far more reach detectors at the surface than would survive if time were absolute. Storage rings accelerate similar particles to near-light speeds and keep them circling for far longer than their rest lifetimes, allowing precise measurements of magnetic properties that would be impossible if time refused to stretch for motion. Light itself bears witness through a shift that owes nothing to wind or medium. When a source moves, its frequency changes for an observer, and part of that change comes purely from time dilation. Even when motion is sideways, with no chase or retreat, the observed color shifts by an amount that depends only on speed. Early precision tests used moving ions and careful spectroscopy to confirm this transverse effect, separating out other contributions until the clean geometric term remained. The result was as expected. Time's rate is bound to motion in a way that light carries plainly. Motion also complicates the act of keeping far-flung instruments in step. Signals must be stamped with times that mean the same thing at both ends, and moving platforms cannot lazily borrow ground clocks as if nothing had changed. Designers account for dilation so that arrays of sensors can combine their data without smearing. A dish on a mountain and a receiver on a ship can share a moment only when both have written geometry into their definitions of now. Without that care, long baselines would lose coherence and precision would fade. Everyday life hides these adjustments because our speeds are small. A car on a highway gathers so nearly the same time as a standing listener that no clock would show the difference without extraordinary patience. Yet the rule is always present, pressing slowly, against thought, even when instruments ignore it. Time stretches for motion, gently and predictably, and our devices are most faithful when they respect that stretch where accuracy matters most. At human scales, the feeling of moving fast is loud muscles and rushing air. At physics scales, the feeling, if it could be felt, is only the accounting of intervals, altering by a factor set by speed. There is no drag in the tick. There is a smaller total count when a swift path returns to meet a slow one. This is why a precise chronology for a flight, a satellite pass, or a particle lap is written with careful attention to the velocities involved. To forget that is to misplace seconds and lose location. Communication across motion requires another grace. When messages travel between frames, senders and receivers must translate. A pulse that launches every fixed fraction of a second in one frame arrives with a different spacing in the other, and conversely. Devices correct for this with formulas that are no more optional than grammar when meaning matters. Deep spacecraft lean on those corrections, and so do networks that synchronize laboratories separated by continents. The rules never sleep, even when the work they protect is quiet. No engine can push a material object to catch the speed of light, because the closer the chase, the larger the factor becomes that slows the clock and thickens the apparent mass of motion. Energy poured in keeps growing the total, yet the speed approaches the limit only asymptotically. This is not a practical barrier built from fear. It is a structural limit that protects causality. If material things could reach or exceed light, the ordering of events would be up for trade, and prediction would become a rumor. The comfort in all of this is that motion's effect on time is not caprice. It follows clean, repeatable patterns that instruments confirm again and again. Radiators in storage rings glow at wavelengths that match their speeds. Decay, curves, integrate to lifetimes, stretched exactly as the fabric's laws calls for them to be. Signals corrected for moving clocks align across distances where uncorrected ones would smear. The world does not mind being measured. It minds only when it is misdescribed, and it answers with patience when asked well. The rule can be phrased in a way that removes paradox from stories about turning around. Proper time is the length of a path through SpaceTime, computed with the metric signature. Between two fixed meetings, the straight time-like path gathers the most proper time. Any detour at high speed shortens that tally. Homebound twins compare notebooks and agree because one path bent and the other did not. No appeal to feelings is required. The difference is a geometric fact about lengths in a space where time and distance share the task. Atmospheric muons make a practical case that fits in the hand. They are born tens of kilometers above sea level when energetic cosmic particles strike air nuclei. A muon at rest vanishes quickly, but many created overhead are moving so fast that, in our frame, their clocks run slow. They reach mountain observatories and sea level counters in numbers that only make sense when the dilation is included. Researchers calibrate instruments with these arrivals, then turn that flux to imaging. By counting how many pass through different thicknesses of rock, they sketch hollows and dense cores inside large structures. The same phenomenon allows imaging of thick structures without drilling. Detectors placed in tunnels or at the base of old pyramids record muons that have survived passage through stone. Fewer arrive along denser lines of sight. The contrast builds a picture of hidden chambers or the fill inside volcanic conduits. The method works because a moving muon's inner clock hands turn slowly for us, preserving its existence over distances it could not otherwise cross. A tiny bit of geometry turns into a survey tool. Storage rings showcase controlled versions on demand. Beams of unstable particles circulate on orbits kept tight by magnetic fields and radio cavities. As speed rises, the bunches experience the accelerating fields differently. because their internal time stretches. A reality designer's right into the timings of the machines. The lengthened lifetimes make delicate measurements possible. Small differences in magnetic moments, precession rates, and emission spectra become accessible because the particles stay around long enough to be asked careful questions. Spectroscopy nails down the kinematic piece by separating it from the push and pull of sources and receivers. Experiments that send light to and from swiftly moving ions measure the frequency shift directly attributable to time dilation. They arrange their apparatus so that the shift remains even when the usual rush toward and fall away contributions cancel. The remaining change matches the exact factor predicted by the geometry. The agreement leaves little room for invention. It is not a mood, it is a measurement. Communications links at high speed fold these adjustments into their protocols without fanfare. Timing beacons aboard aircraft and ships encode their motion into the way they report time. And receivers translate the report back into a shared clock that aligns within strict margins. Planetary radar, which bounces pulses off nearby worlds, includes both motion-driven dilation and travel time effects when scheduling receptions. The pulses arrive when booked because the model for time respects the different paths. A quiet principle sits beneath these examples. The rate of a good clock depends on its instantaneous speed and gravitational environment, not on how gently or harshly it turns. Acceleration by itself does not make a well-behaved atomic clock miscount beyond what its momentary velocity and depth predict. This clock hypothesis has been checked to high precision by comparing devices on fast-rotating tables with matched devices kept still. The rates agree with the speed-based formula within experimental margins. Edges of feasibility push the rule without breaking it. Particle factories raise energies so high that radiated light from bending paths shifts into wavelengths human eyes can see, turning invisible beams into glowing halos. The color and power depend on speed in ways the equations lay out in calm algebra. As researchers tune, the light answers, moving along the spectrum and confirming again that time's pace is tied to motion. Even the heating of the ring's vacuum chamber follows from these relations, narrowing when speed steps down and swelling when it rises. Behind every clean conformation lies a feeling that matters for rest. The universe does not punish motion with confusion. It provides a schedule. Go faster, and the schedule stretches. Go gently, and the schedule fills with more moments. Devices that respect the schedule work, and arguments about what time really is grow quiet. Two friends who parted and meet again, compare minutes, and find harmony in the difference because they understand the path each took. In that understanding lies a steadiness suited to sleep. If one image may sit quietly beside these facts, think of a hallway where footsteps echo from the far end. Begin to run, and the echoes return farther apart to a listener standing by the door, even though your own rhythm under your ribs has not changed its count. Two truths remain compatible. Inside, the pace feels steady. Outside, the intervals lengthen. Motion slows the time you bring back when paths meet again. Accepting that turns argument into clarity and makes room for rest. Sleep can follow schedules too, gently, without clocks or alarms. Depth in a gravitational field changes the pace of clocks. The rule is direct. Deeper means slower, higher means faster, as judged from a common reference. This is not a trick of instruments. It is how space-time parcels out duration in places. Where the map bends inward, a clock taken downward and returned will have counted fewer beats than its partner left above. Two devices built alike and kept apart at different depths will drift apart by a steady, predictable amount. The difference is small, near Earth's surface, yet not zero, and it scales in ways that have been checked with care. A classic ground test used a quiet hallway and a patient source of gamma rays. A beam sent upward gained a tiny energy because lower clocks ticked more slowly than higher ones. The shift matched the value expected from the local gravity and the height of the apparatus. It was an early, compact confirmation that time feels weight. Later, fountains of cold atoms measured the same effect over meters with far greater sensitivity, showing that a change of elevation, you could step in a breath, alters the rate by a measurable fraction. Orbiting clocks put these facts to work every minute. Satellites circle above much of Earth's pull while moving briskly along their paths. Motion alone would slow their tick relative to clocks on the ground. Reduced pull alone would quicken it. The two influences do not cancel. Their combined difference amounts to roughly a few dozen millionths of a second per day. Left uncorrected, that drift would spread position fixes by kilometers within a single day. Designers pre-adjust spaceborne clocks and apply ongoing corrections so receivers can place a phone or a ship within meters. Astronomers find gravity's effect on time written in light from compact stars. Spectral lines from white dwarfs arrive, shifted toward longer wavelengths because light climbs out of a deeper well before reaching us. The shift is not from the star's breeze or our own motion. It is a gravitational redshift tied to the mass and size of the dwarf. The same principle turns pulse arrival times in tight binary systems into tests of curved time. As a pulse passes near a companion's well, its journey lengthens a little. The timing reveals the depth without touching the source. Networks of laboratory clocks trace gravity's hand on rates across continents. Optical devices that count the wiggle of light trapped in lattices keep time so precisely that a difference of a few centimeters in height changes their tally in a measurable way. Physicists link them with fiber and compare, watching the Earth's field write a soft signature into the counts. Over months, the pattern of changes can reveal groundwater movement, heavy snowfall, or the swelling of a volcano's flanks. Time becomes a survey instrument, sensitive to quiet shifts inside the planet. The same sensitivity refines surveying. Portable clocks carried up towers or down shafts compare their totals against a base clock and report depth differences as time offsets. Because the effect depends on the gravitational potential and not merely distance from the center, maps based on timing reveal features that weight alone might miss. The method is young, but it draws strength from the same rule that guides the sky, where depth changes, rhythm changes, and careful counting makes the change visible. In deep gravity, the pacing difference is extreme. Near a collapsed object with an event boundary, a clock held steady outside runs faster than one held closer in, and the ratio can become astonishing. To a far observer, signals from just above the boundary take longer and longer to clear, stretching into silence as their color slides beyond reach. For the object sending them, moments pass normally. The divergence lies in the paths through the map. No magic occurs at the surface. Comparison creates the strangeness. Elsewhere in the cosmos, the effect writes small but crucial corrections into stories we tell with light. Gas orbiting a compact star emits radiation, whose energy carries a blend of motion and depth. By untangling that blend, astronomers learn mass and size, and they test whether the curved framework near the surface matches expectation. Neutron stars, with their enormous density, twist time so strongly that pulses from their caps arrive early or late by tiny amounts, as the orbit carries them through regions of different depth. The pattern is a fingerprint of the well itself. The practical lesson does not require equations. Whenever clocks must agree across different levels on a mountain observatory, in a valley lab, aboard a craft above the atmosphere, designers include depth and speed in the timing budget. They do it quietly because it has become routine. Tracking stations schedule contacts with care for when signals will crest the horizon and when they will be delayed by the bend. Airlines lean on systems that already fold timing and route into one answer, guiding paths across air and ocean. One rocket experiment carried a hydrogen maser upward for a brief flight and compared its rate with a twin kept on the ground. During ascent, at apogee, and on return, the airborne clock's tick followed the predictions for depth and speed together within narrow uncertainty. The agreement turned a blackboard term into a measured pattern written against the sky. Solar spectra offer another confirmation. Light formed deep in the sun's well climbs outward through layers before crossing space. Its features arrive shifted by precisely the amount expected from the star's gravity. The Earth's field is not uniform. Rotation causes the planet to bulge slightly at the equator, and mass is not distributed evenly beneath oceans and continents. As a result, the surface of equal potential that seawater would follow, the geoid, deviates from a simple sphere. Clocks resting on different parts of that surface run at slightly different rates, even when they stand at the same height above a geometric ellipsoid. Timing networks reference the geoid to define a practical level, and surveys that tie regions together adopt that surface, so comparisons make sense. Navigation satellites demonstrate how these ideas become daily utilities. Hardware aboard each craft is tuned so that, once in orbit, its tick matches a standard defined on the ground after both depth and motion are counted. Receivers use signals from several satellites at once to solve for position and time, adjusting for travel delays through the atmosphere and for the small relativistic offsets that build as the geometry changes during each pass. The adjustment is modest in fraction and enormous in effect. Without it, maps would wander and guidance would lose faith in itself. Precision laboratories push the sensitivity further still. Optical lattice clocks have stabilities so fine that carrying one up a staircase produces a measurable difference in the tally after a short rest. Linking such devices across cities lets researchers watch tiny shifts in the geoid as subterranean water moves or as seasonal snowpacks load and release. The planet writes its changes into time, and the readout arrives as calmly as the digits on the display. In stellar remnants, gravity's influence on time becomes a tool for weighing. White dwarfs show a redshift that depends on their mass and compactness. Neutron stars amplify the effect until it threads through every story about their signals. When two such stars orbit closely, the timing of their pulses gives access to the spacetime they share, confirming that clocks near intense gravity slow by factors that would be undetectable in any human setting. The data arrive as arrival times and profiles, unromantic and decisive. Depth also touches the orbits of artificial moons in subtle ways. As a satellite moves through Earth's slightly lumpy field, its altitude and speed adjust, and with them the rate of its onboard clock. Ground stations predict these variations and command updates when needed. The coordination resembles breathing inhale on approach, exhale after pass, keeping time and trajectory in quiet synchronization. The rest is patience, calibration, and trust between distant clocks always. Light does not detour because of a hidden chord. It follows the geometry it finds. A beam launched across apparently empty space travels along the easiest route allowed by the map. Near mass, that map curves, and the route narrows or widens in subtle ways that steer the beam by a small, measurable angle. Astronomers tested this calmly with starlight that grazed the sun during a total eclipse many decades ago, comparing positions recorded with the sun elsewhere in the sky to positions taken with sunlight blocked. The stars appeared displaced by an amount predicted by curved structure, confirming that gravity works by shaping paths rather than tugging at distance. Radio astronomers repeat the measurement with signals that skim the solar rim, and with precise timing of spacecraft links as they pass behind planets. The delays and deflections are not guesses. They are numbers that match a rule. Mass reshapes how distances and durations cooperate, and light obeys that cooperation without complaint. On cosmic scales, bending becomes a lens. Galaxy clusters, heavy with stars, gas, and unseen matter, warp the images of more distant galaxies lined up behind them. Where alignment is close and mass is concentrated, arcs and multiple copies of the same background source appear. These are examples of strong lensing. Where alignment is broader and mass is spread, the effect is smaller and statistical. Galaxy shapes are sheared by tiny amounts that, when averaged across wide fields, trace the pattern of mass in front. That is weak lensing. Both forms treat light as an honest messenger and the sky as a sheet marked by curves. The outcome is a map that tallies what shines and what remains dark, because both contribute to bending. In this way, lensing counts mass without assuming how gas should glow or how stars should orbit. It weighs structures by how they change routes, not by how they color the night. Lensing also times the universe. Light from a distant quasar can travel to us along several curved routes past an intervening mass. Each route has a different length and passes through regions where time flows at slightly different rates. When the quasar flickers, the images in the lens flicker at different moments. Those delays encode distances in a way that, with careful modeling, helps calibrate the scale of cosmic expansion. The same logic measures cluster masses directly from their lensing pattern, without relying on the temperature of hot gas or the speed of orbiting galaxies. It is a clean method. Record the distortions, fit the geometry, and read the mass. When surveys cover large areas with deep exposures, the network of tiny shears becomes a chart of filaments and voids, a picture of where matter gathered and where it did not. At smaller scales, lensing reveals objects too faint or too compact to see otherwise. A star passing in front of a more distant star can increase the background star's brightness for a short time, because the nearer star's gravity focuses the light. This is microlensing. It does not require the nearer star to glow. It requires only a steady alignment and an exact geometry. In this way, planets have been found around stars thousands of light years away, and solitary dark remnants have been weighed by their effect on background light. The measurements depend on curves, not colors. They turn motion across the sky into a temporary lens, writing mass into brightening and fading. Even the oldest light we can see, the faint afterglow from the early universe, is lensed. Its pattern is subtly smeared by structures that formed later, adding a specific signature that helps chart how matter was arranged on long scales. Observers model that smearing to refine their view of both the ancient light and the younger structures in front of it. The same sky thus serves as both a relic and a tool, with lensing as the language that lets the two speak to each other, because lensing's strength depends on distances between source, lens, and observer, combining different populations nearby. Galaxies, distant galaxies, and background radiation separates how mass grew from how distances stretched. The method checks gravity itself. If the rule for curvature changed on the largest scales, lensing patterns would deviate from predictions built on the same spacetime map that explains orbits and time delays. Surveys test this by comparing how matter clusters with how it lenses. So far, the language is consistent. The same quiet equation that makes a planet's path curve explains the arcs around galaxy clusters and the soft shears across deep fields. Where tension appears in parameters derived from different methods, lensing offers an independent cross-check, tightening uncertainties and guiding improvements in models and instruments. Every application depends on measurement discipline. Telescopes must resolve faint smudges without adding their own distortions. Detectors must hold calibration across seasons so that shape changes in galaxies to record the sky, not the camera. Atmospheric shimmer must be modeled or averaged so that it does not mimic shear. Teams build image simulations to learn how pipelines respond. They compare overlapping fields and different filters to ensure that results do not hinge on a single choice. In this way, lensing becomes both a science and a practice, a series of steps that return to the same conclusion from many directions. The human value in this is steadiness. Lensing does not give answers because someone wishes to see a certain pattern. It gives them because light has no pride and will follow the map you give it. When the map curves, beams agree. When the map lies flat, they pass unchanged. The response is mechanical and therefore dependable. That dependability turns long exposure and quiet counting into a picture of something we cannot touch. It turns patience into a measuring stick. It lets us believe, gently, that the world can be read without hurry and the truths written in geometry will wait for us to arrive. Imagine a sheet of clear resin that is set with tiny invisible ripples. Hold it over a page of text. Letters at the edge stretch a little and dots become slight ovals. The ink did not change, the path did. Gravitational lensing is that resin on the sky. We learn the ripples by how they stretch what lies behind, and when we have learned them well, we lift the sheet in our minds and see the page more clearly. That single image is enough. Return to the facts. Rays follow geodesics. Mass shapes those geodesics. The shapes reveal mass. The tally is honest. The night can keep its quiet, while the measurements keep their truth. And as the thought settles, so does the breath, as if the mind itself were following the easiest path through a shaped, generous world. Accelerating mass disturbs space-time in a way that travels outward as waves. These disturbances move at light speed and carry energy from their source, thinning as they spread. A pair of compact objects locked in a tight orbit is an efficient maker of such waves. As they circle, the orbit shrinks slowly. The frequency rises, the amplitude grows, and the entire pattern sweeps upward like a musical chirp. Observatories designed to listen for such changes use laser beams sent down long perpendicular tunnels. Mirrors hang on fine suspensions at the ends. When a wave passes, one arm lengthens while the other shortens by less than the width of a proton. The beams recombine at a detector that translates the tiny change into a trace. Environmental noise is measured and removed with care so that what remains can be trusted. The first signal to clear all tests came from two heavy black holes that merged far away. The trace matched the shape predicted by numerical solutions to the same equations that guide orbits and bending. No light was needed to verify the event. The wave itself carried the story: masses, spins, distance, and the four. Time, the final ringdown, faded. Independent observatories confirmed the pattern, ruling out local disturbances and grounding the detection in agreement. Since then, many mergers have been recorded. Some involved heavier pairs, some involved lighter pairs. A different class of detectors, sensitive at other frequencies, listens for waves from neutron stars and for a background formed by many faraway sources overlapping. These waves do more than mark events. In favorable cases, the shape of the trace encodes how far the source lies without needing a separate calibration. The signal provides a distance measure that can be compared with whatever light counterpart appears, if any, to learn about expansion in another way. When waves and light from the same event arrive nearly together, the closeness of their arrival constrains how both travel, The agreement so far shows that these waves move at the same pace as light through the fabric, strengthening confidence that the geometry treats both messengers equally on their long journey. Binary neutron stars add another layer of information. When they merge, they can launch matter rich in heavy elements, producing a glow that brightens and fades across days. If telescopes catch that glow, the position of the source on the sky becomes known precisely, and the wave trace can be matched to a host galaxy with a redshift. The pair of measurements, distance from the wave and redshift from the host, ties wave astronomy to expansion history. In this way, ripples in space-time join candles and rulers in the quiet task of measuring how the universe has stretched. Listening for waves requires long periods of steadiness. The instruments must hold their alignment across seasons. Laser frequencies must remain stable, and mirrors must stay isolated from ground, tremor, wind, and thermal creep. Teams model and subtract motions from passing weather, distant surf, and vehicles. Calibration lines are injected to verify that sensitivity and response match expectations. Unexpected features in the spectrum are traced to their causes and removed, leaving a band in which wave signals can stand out. Once detection is made, the collaboration shares sky maps with telescopes that respond, turning the earliest ping into a coordinated search for counterparts. Waves also test how gravity behaves when fields are strong and changing quickly, a regime distinct from steady orbits or gentle bending. The agreement between traces and predictions shows that the same theory that bends starlight and slows time also handles collisions where space-time itself vibrates. The consistency across these regimes is not assumed. It is checked with every new event, and small differences become opportunities to refine modeling of spins, orientations, and the matter left behind. For black hole pairs, the final object rings like a struck bell, with tones set by mass and rotation. Measuring those tones tests whether the horizon behaves as expected. For neutron-star pairs, the phase just before merger depends on how compressible dense matter is, a property that standard telescopes cannot easily measure. A separate listening strategy tracks slower, longer waves by watching how the arrival times of regular pulses from spinning neutron stars wander together. If a background of long wavelength waves passes through our region, many lines of sight will stretch and compress in a correlated way. The timing of the pulses carries that pattern. Observatories that monitor these millisecond clocks keep records for years, looking for a signal that appears not in a single trace, but in the shared sway of many. Early hints guide patience, accumulating data decides. The scale probed by such methods fills in the spectrum, reaching to frequencies far below what ground instruments can manage. The language of waves reaches beyond collisions. Supernovae that release a stellar core's pressure in a heartbeat should shake the surrounding fabric. Though the signals may be faint and messy, asymmetries in rapidly rotating remnants could send a steady hum if imperfections persist. The pursuit of these signals pushes instruments toward quieter operation and longer coherence. Even when silence follows a candidate event, the limits set by not hearing a wave teach something about how the explosion was shaped and how matter moved inside it. What waves offer to feeling is a different sense of openness. Light sees what glows and what gas allows through. Waves cross dust and fields without scattering. They carry the imprint of the motion that made them, not the colors of what lies between. A catalogue of such traces becomes a record of how often heavy pairs form, how quickly they meet, and how their spins align. When catalogues from many sources and methods are combined, the story of stellar life and death becomes rounder, less dependent on any single messenger, and more faithful to the variety of ways matter moves. It is important that instruments do not demand attention from those they serve. They hum in quiet buildings with long arms aligned across planes. They spend most days listening to nothing that warrants an alert, because the sky is silent in most directions most of the time. The value lies in being ready for the moment when a ripple passes, and in having built a chain of trust such that a ping in one hall can be believed by a room of distant mirrors in the same breath. The world does not often offer that kind of coordination. Physics does, by giving all rooms the same rules and all beams the same behavior. It is a simple comfort that has earned its place. If a single image can accompany these facts without crowding them, picture a still lake under moonlight, where a single unseen swimmer turns near the center. The rings that reach the shore are faint, regular, and widening. By their spacing and their speed, a listener can tell how strong the stroke was and how near the turn. That is enough. Under that image, return to the pie. Quiet account. Accelerating mass radiates. Waves travel at light's pace. Instruments translate vanishingly small. Changes into traces. Traces give masses, spins, distances, and tests. Some events add light, some do not. Together, they make a new astronomy that hears where once we only saw. In that steady hearing, there is room for rest. The mind can set the trace aside and keep only the assurance that the universe moves with patterns we can detect gently, and that patience is rewarded in time. A black hole forms when collapse continues beyond the reach of pressure. Matter compacts until escape paths for light converge and close. The surface that separates what can return from what cannot is called the event horizon. It is not a shell or skin. It is a boundary traced by the geometry itself. A traveler falling freely across it feels no sudden shock, no scrape against a surface, only the same smooth pull that guided the fall all along. Far away, the same crossing looks different. Light sent outward from near the boundary redshifts, losing energy as it climbs, and its pulses spread until they are too stretched to collect. Two stories remain compatible because they belong to different frames. Local physics continues without drama. Distant clocks record a slow fade that never quite shows the crossing. Inside, the roots of time point inward. Every possible time-like path leads toward the center. Classical solutions sketch a point where curvature diverges and the equations surrender. Quantum gravity tries to mend that breakdown by replacing the singular center with something finite, but the complete account is unfinished. Observations, therefore, focus on the region outside the horizon, where predictions are clear. Stars near the centers of galaxies orbit unseen masses that act like single compact objects. Their paths fit a central mass that outstrips any cluster of smaller bodies, and the neatness persists as the orbits shrink. The simplest reading is that a collapsed object sits there, silent at its boundary and decisive in its pull. The space around such an object shines for its own reasons. Gas falling inward converts gravitational energy to heat as it squeezes and shears. The glow stretches from radio to high-energy X-rays, with details set by density, temperature, and speed. Magnetic fields twist through the flow, tapping rotation and guiding a fraction of the infall into narrow jets. Those jets can extend far beyond their birthplace, crossing interstellar and intergalactic space, brightening at shocks, bending where pressure changes, and marking the direction of the engine long after the inner supply wanes. Timing in the radiation helps diagnose the neighborhood. When brightness rises and falls in repeating ways, the periods point to orbits near the innermost stable circular path. Faster rotation pulls that path inward and alters the sequence of heating and cooling. A change instruments can track. Images sharpen the picture. Linking radio dishes across continents, yields resolving power high enough to outline structures on horizon scales. Patterns reconstructed from phase-linked signals show rings and dim centers, consistent with light that grazes the photon orbit before departing, and with an interior where emissivity drops. The ring's size and shape test the mass and spin inferred from motion. Agreement among these measures builds confidence that the geometry close to the boundary matches the expected rotating solution. Polarization maps add magnetic geometry to the scene, tracing how fields thread the gas as it swirls and falls. Accretion is rarely steady. Clumps of hotter plasma orbit and shear apart, and their flares pass in ways that encode radius and speed. Spectral lines formed by heavy atoms in the inner flow arrive broadened and skewed by depth and motion. Red wings extend because photons born deep within climb out along longer paths. Blue horns mark material racing toward us on the near side of the disk. Fitting these profiles yields radii and inclinations, and those in turn tie back to spin and mass. No single diagnostic stands alone. Timing, spectrum, polarization, and imaging cooperate, and the agreement matters more than any single result. At smaller distances and shorter timescales, binaries, where a compact object feeds from a normal star display, cycles. As material builds in the disk and then plunges inward, the emission passes through distinct states, each with characteristic hardness and timing, and noise. The alternation repeats with some irregularity, yet the underlying pattern persists. The states are reflections of how energy is divided between hot inner regions and cooler outer layers, and of how the last stable orbit sets the inner boundary for efficient radiation. Astronomers use these cycles to weigh the compact object and to estimate its spin, guided by models that respect the local geometry. Not all boundaries of communication belong to collapsed stars. In an expanding universe, there exists a world-line-dependent limit beyond which light emitted today will never arrive, because the scale between source and observer grows too quickly. That horizon is not linked to a mass. It is set by the expansion history. It limits the portion of the cosmos any one observer can ever influence or survey. The mechanism differs from a black hole's boundary, but the lesson is similar. Causality draws an edge across maps, and edges matter. They say what can be known directly and what can only be inferred. The absence of light from within a horizon does not make the boundary meaningless. Surroundings speak for it. Orbits of nearby stars confine the mass. Hot gas draws a temperature profile that tightens the estimate. Maser spots in rotating disks trace curves that remain narrow to radii too small to be anything but compact. And on the largest baselines, rings and shadows appear exactly where they should if photons circle before escape. The silence inside is part of the message, made legible by the eloquence of what remains outside. Quantum fields, in curved spaces, predict a thin glow near horizons. Virtual pairs can separate. One quantum departs, the other subtracts energy from the mass. The process is unimaginably slow for large objects, a drift rather than a blaze. The spectrum, measured from far away, resembles the warmth of a body whose temperature depends on the boundary's size. For stellar remnants, the effect is invisible against ambient backgrounds. For hypothetical tiny remnants, it would be stronger, but no such objects have announced themselves. The idea, nonetheless, organizes thought about entropy and information, tying surface area to the count of microstates, and reminding us that gravity, thermodynamics, and quantum rules share a long border. Close to the boundary, the rules for paths shape how we interpret what we see. Light can orbit temporarily, circling more than once before departure, and those loops produce lensed features in the image. Matter spirals down through a sequence set by stability. The innermost stable orbit is a threshold. Inside it, circular paths cannot persist. That radius moves inward with aligned spin, outward with counter-rotation, changing how efficiently infalling gas radiates. Observers read those shifts in timing and spectrum, then compare them with images, and the triangulation narrows uncertainties that any one method would leave wide. One can keep a soft picture without losing the science. Think of a deep, perfectly round well hidden beneath flat grass. You speak toward it and hear nothing return, not because air swallowed the sound, but because the shape admits no echo from the depth. The refusal to answer is itself information about form. Horizons behave similarly. Their quiet is a sign, and the neighborhood's response, motion, heat, polarization, silhouette, fills the rest of the page. The lesson is patient and does not demand certainty from unfinished theories. It allows a gentle admission. Beyond some lines we read by shadows, and the shadows are enough to guide us to sleep. Rotation alters space-time around a massive body by a small but measurable degree. The local standard of rest, the set of directions that would define not turning, is drawn slightly along with the source's spin. This effect, called frame dragging, changes how gyroscopes point and how nodes of orbits drift. A gyroscope in a quiet polar orbit does not keep faith with a distant star forever. Its axis precesses by a calculable amount that depends on the central body's mass and spin. Instruments have measured this near Earth by floating superconducting rotors that were shielded from every disturbance except the tiny precession predicted by the fabric's equations. Laser ranging to passive satellites confirms related nodal shifts, turning motion of polished spheres into a test of rotation written into space-time itself. Around a rapidly spinning black hole, the twist amplifies. There exists a region outside the horizon where all observers are compelled to co-rotate relative to infinity. This domain is the ergosphere. Inside it, no stationary world line exists. All time-like routes include a share of the spin. The boundary's location depends on latitude, touching the horizon at the poles and bulging outward at the equator. In that environment, energy and angular momentum can be exchanged in ways forbidden around non-rotating solutions. Carefully arranged particle paths or magnetized flows can, in principle, extract rotational energy, reducing the spin while feeding outflows. The innermost stable circular orbit sits closer to the horizon when the orbit aligns with spin, and farther away when it opposes it, shifting how matter radiates while falling. These twists leave signatures, orbits that would otherwise remain fixed in orientation precess. A satellite's ascending node drifts over time, and the pericenter advances. Correcting for Earth's shape, atmospheric drag, and solar radiation pressure leaves a residual, consistent with frame dragging's gentle pull. In rings around compact objects, quasi-periodic signals in brightness carry frequencies linked to epicyclic motions that depend on spin and radius. Fitting those frequencies places the rotating solution into numbers, giving estimates of spin that agree with independent spectral and timing methods. Jets from the vicinity of spinning holes likely borrow power from both rotation and magnetic fields. If field lines thread the ergosphere and connect to distant plasma, the twisting of space-time helps launch collimated streams that hold together for great distances. Observers test these ideas by measuring jet speeds through apparent motion, by tracking polarization that maps field direction, and by watching how knots brighten and fade as shocks pass. Small changes in orientation can produce large differences in brightness when speeds approach light. So complete models must include geometry, spin, and beaming. Agreement across many systems suggests that the engine couples rotation to fields in a way that holds across mass scales. Engineers meet frame dragging as a correction term, not a curiosity. When missions require millimeter precision over long arcs, neglecting the twist leads to measurable error. High-precision orbits included, along with other relativistic adjustments. The term's smallness near Earth does not make it ignorable. It is added because attention to detail earns success. In the same way, ground networks that time signals across long baselines apply tiny corrections for rotation-related effects so that clocks agree when they meet again on paper. These are not philosophical gestures. They are the small arithmetic of a world that enforces fairness through structure. The twist changes intuition about rest. In Newtonian thought, a distant star fixes directions for gyroscopes forever. In the rotating solution, mass and spin leave their autograph on local standards. A perfect gyroscope in orbit, freed from friction and shielded from fields, slowly writes a circle on the sky because space-time itself carries an eddy. The motion is not a force acting through a medium. It is the geometry telling inertial frames how to orient as they slide around the rotating source. The difference matters near compact objects, where the twist is strong enough to rearrange orbits and to squeeze the gap between the last stable path and the horizon until they nearly touch. Inside the ergosphere, exotic exchanges become possible. Particles can enter with one energy and exit with more, leaving a negative energy partner that crosses the horizon. In practice, magnetic fields and plasma flows provide the more robust channels for energy extraction. But the kinematic idea clarifies what spin makes room for. Numerical models thread rotating holes with fields and allow plasma to organize into funnels. The outflows that result carry power consistent with observed jets, and the efficiencies match the sense that spin, field strength, and disk thickness all shape the outcome. Evidence for frame dragging beyond Earth comes from timing in accreting systems. When a star feeds a compact partner, flickers at specific frequencies appear in the light curve. The pattern shifts with accretion rate, and the favored interpretation ties the frequencies to precession modes in a tilted flow. The precession rate depends on spin and radius, and fitting the changes across states gives a consistent estimate. As with all such work, the power lies not in a single light curve, but in how several lines of evidence converge. Gyroscope data near Earth, nodal drifts from lasers, timing near compact objects, polarization maps of jets, and the radii inferred from broad spectral lines. A visual that stays gentle is a pot of syrup stirred slowly. The surface drags the nearby swirls into motion, even when those swirls began at rest. Farther out, the pull fades. Nothing sudden occurs. The turn grows with closeness to the spoon. Space-time responds to rotation with the same restraint. Frames near the source are carried a little, then a little more, and finally so much that standing still becomes impossible. The picture is plain, and the numbers built upon it are careful. Together, they let a listener rest with the idea that even small twists can guide long paths when you wait long enough. Galaxies drift apart, not because they rush through a pre-existing emptiness, but because the scale of space-time itself grows. Distances between far-flung clusters lengthen as the metric stretches, while systems bound tightly by gravity galaxies, groups, and the solar family remain intact. Observations relate recessional velocity to distance with a simple proportional trend at modest ranges. That relation, found by mapping spectra and brightness, signaled that the universe is expanding and offered a way to estimate ages and sizes beyond guesswork. The visible sign is redshift. Wavelengths arriving from afar are longer than when they left, because the space they crossed expanded as they traveled. No vantage point sits at the middle of this growth. Every observer, wherever they stand, sees distant galaxies receding on average, and the same rule ties velocity to distance in every direction when local motions are averaged away. Expansion is a property of the whole, not a privilege of one place. On small scales, gravity holds sway, binding stars into galaxies and galaxies into groups. On scales of hundreds of millions of light-years, the stretch dominates, and matter settles into a web of filaments and voids that reflects how initial fluctuations grew under the rules of gravity and expansion together. Light carries time with it. Because signals take time to arrive, distant objects are seen as they were when the universe was younger and denser. This ladder of distance and age lets astronomers reconstruct expansion history. Standardizable supernovae provide beacons whose peak brightness can be inferred from the shape of their light curves, turning apparent brightness into distance. Ripples in the distribution of galaxies, relics of sound waves frozen when atoms formed, give a characteristic scale that can be measured across cosmic time. The ancient background radiation records conditions when the universe was still a hot, uniform plasma, and the pattern of its small temperature variations encodes the shape and contents of the cosmos. Each method carries its own uncertainties, yet together they point toward a consistent story of growth. The rate of expansion has changed over time. Early on, matter slowed the growth, and structures formed as gravity pulled on small overdensities. Later, observations revealed an unexpected twist. Distant beacons appeared dimmer than they would if the slowdown had continued unchanged, implying that expansion has sped up in more recent epochs. The simplest representation of this behavior is a constant energy density associated with empty space itself, a term that acts like pressure that pushes rather than pulls. Whether this dark energy is truly constant or hides dynamics of its own remains an open question, but the effect on distances is measurable and has been measured in several independent ways. Expansion does not tear bound systems apart. The Earth does not spiral from the Sun, and the galaxy does not unravel into a spray. Gravity inside these structures overwhelms the small global stretch. The rule acts on large scales, where average densities are low and binding is weak. This separation of scales resolves a common worry and keeps daily life comfortably detached from cosmic motion. The stretch is something you read in spectra and number in surveys, not something you feel in your hands. Uniformity at large scales is another measured feature. When maps reach far enough, the average looks the same in every direction and at every place, aside from the patterns carved by the web. This homogeneity and isotropy give simple equations room to work. Small departures from perfect uniformity are the seeds from which structure grew, and their spectrum, how much power sits on each scale, matches the picture that inflationary physics sketched for the earliest moments. In that sketch, the universe underwent a brief, rapid expansion that smoothed curvature and spread quantum fluctuations across macroscopic distances. Details remain under study, yet the measured uniformity and the specific pattern of small anisotropies tend to support the outline. Distances in an expanding cosmos come in several flavors. The distance you would measure with a ruler laid down in the present is not the same as the distance inferred from a source's apparent brightness or its angular size. Each definition depends on the path the light took and on how the scale factor changed while it traveled. Astronomers use the correct form for the measurement at hand, translating among them to ensure that counts of galaxies, angles of features, and brightnesses of candles all speak the same language. The care is necessary because the differences are not small at large look-back times. The idea of center dissolves when the whole stretches uniformly. Asking where the expansion began is like asking which raisin in a swelling loaf marks the origin. Every point was once closer to every other because the scale was smaller. No point owns the beginning. The story belongs to the entire fabric. The same picture clarifies why there is no edge in the usual sense. The part we can see is bounded by how far light has reached since the hot, dense beginning. Beyond that limit lies more of the same, not a wall. The horizon grows with time as more distant regions come into view. Growth affects light itself. As space stretches, wavelengths stretch, and colors shift toward the red. That shift is not a wind against the beam. It is an honest record of the distance scale changing during flight. Because the effect is systematic, it becomes a ruler. Measure the shift, compare it with independent distances, and learn the rate at which the scale has changed. Apply the procedure across many depths, and the temporal behavior emerges, with early slowing and later speeding both written into the graph. Cross-checks with the ancient background and with ripples in galaxy clustering keep the reconstruction honest. A gentle image can sit beside the facts without leading them. Picture dots in a rising loaf of bread. As the dough swells, the dots separate, even though none glides across the surface. No dot sits at the special place where swelling begins. The oven warms everything, and distance grows everywhere at once. That is how expansion works. It is a property of the baking, not a parade of dots marching across a tray. Bound pockets bubbles in the analogy can hold their shape inside the loaf, just as galaxies hold together against the global swell. The picture is humble and enough. Instruments turn this understanding into numbers by surveying the sky with patience. Spectrographs measure redshifts for millions of galaxies and quasars. Cameras record shapes and brightnesses across wide fields. Microwave receivers map the ancient background, subtracting foregrounds and checking calibrations by switching between patches of sky. The work is procedural and careful. When new tensions appear between methods, when one route to the rate of expansion disagrees modestly with another experiment's sharpen, the answer will come not from declaring a winner, but from combining data in ways that expose overlooked systematics or reveal new physics. All of that can proceed without hurry. If this feels large to hold, it can also be gentle. Expansion does not ask you to solve it in the dark. It asks only that you accept that distances grow on the biggest scales while the near world remains familiar. You can let the mind drift with that idea the way you watch a slow tide fill a bay. Boats at anchor ride the rise without leaving their moorings. Far markers drift apart. Somewhere beyond the headland, swells run. Somewhere beyond what we can see, more coastline waits. The rhythm belongs to the whole water. That is enough to sleep on. Late in the last century, astronomers measured explosions from distant galaxies and found them fainter than a steadily slowing universe would allow. Those events, supernovae with remarkably similar peak brightness, serve as beacons whose apparent dimness translates into distance. The pattern they traced implied that long ago the growth of distance slowed under gravity's pull. Yet later the slowing eased and the cosmic scale began to increase more quickly. To account for that change, cosmologists added a term that behaves like a uniform energy density with negative pressure. In the equations, such pressure does not draw, it drives. The simplest version is a constant embedded in the field relations themselves, a possibility the mathematics allowed from the beginning, even before evidence asked for it. Other lines of observation tell a compatible story. Ripples, recorded in the ancient light, provide a standard length that appears again in today's galaxy patterns. The way that ruler looks at different depths requires a smooth ingredient that does not clump like matter does. Maps of weak gravitational lensing, tiny shape changes in distant galaxies caused by intervening mass, agree more cleanly when a uniform component contributes to the background against which structure grows. With that ingredient present, simulated universes mature into webs that resemble surveys, and the expansion history reconstructed from several methods becomes self-consistent within uncertainties. The origin at the microphysical level remains uncertain. The behavior at the large scale is described well. A pervasive presence fills space and makes the scale factor increase at a rate that gradually rises with time. Consequences are measured and modest in their daily meaning. Farther galaxies will keep increasing their redshifts until light they emit in the deep future can no longer reach us, not because it slows, but because the distance to cross enlarges faster than the signal can advance. Regions already knit tightly by gravity, stellar systems, galaxies, bound groups, remain intact, their internal pulls dwarfing the gentle push written into the whole. In the widest view, the catalogue of very remote sources thins. Deep exposures reveal fewer new arrivals simply because fewer remain within the part of the universe that can still talk to us. Nearby structures keep orbiting, colliding, and merging in familiar ways. The change is not a drama. It is a temperament the universe adopted quietly and will likely keep for a long while. Evidence beyond distance ladders supports the constant's temperament. The pattern of small temperature variations in the ancient radiation sets precise conditions for geometry and contents. Fits that include a uniform energy density find the large-scale curvature to be close to flat on average, while matter and radiation together fall short of that total. The remainder is the smooth term. Measurements of galaxy clustering at many depths, when translated using that same standard length, follow curves that rise and bend in ways that match an accelerating scale factor. None of these analyses require exotic assumptions about light or dust to mimic dimming. Each uses independent anchors, brightness histories, angular sizes, shape statistics to arrive at the same quiet conclusion. The uniform energy does not operate like a field coiling around sources. It looks identical in every direction and at every place when averaged over large volumes. That symmetry is why it does not gather into clouds or threads, and why its effect appears not as a local push on particular objects, but as a contribution to the background against which all distances evolve. Its density remains roughly the same while matter thins as space grows, so its influence strengthens relative to the rest as ages pass. In a very distant tomorrow, when most structures drift beyond each other's reach, the local sky will still hold stars bound into whatever long-lived islands remain. The large-scale quiet will be the absence of new messages, not the silence of nearby life. The term simplicity invites caution and acceptance in equal shares. There are models in which the smooth energy varies slowly, or in which gravity itself changes at the longest scales, in ways that mimic a push. Experiments and surveys look for those signatures. So far, the constant fits well. If a future refinement reveals motion in the uniform term, the change will be measured and absorbed the way earlier adjustments were. Until then, the constant behaves like frost, forming evenly on glass, an even layer that changes how light passes without favoring one corner. The pain remains, clarity shifts. That is the tone of this pressure: impartial, widespread, and dependable. One more implication is gentle and worth holding. In such a universe, each observer carries a private horizon that grows toward, but never catches, certain receding regions. That horizon is not a wall. It is a boundary drawn by time and the rate at which space grows. Beyond it, other horizons crisscross, each centered on a different place, each enclosing a different share of the whole. The idea is not lonely. It clarifies that what we measure is always a slice through a larger fabric, and that slices are enough to tell a coherent story when compared with patience. Instrumentally, the uniform energy appears not in a single sensor, but in many comparisons done carefully. Teams measure distances with supernovae whose light curves are standardized, then cross-check with galaxy ripples that preserve an ancient sound scale. They map subtle shears over millions of shapes, subtracting instrument signatures until only sky remains. They fit background radiation patterns with models that make independent predictions for other observations. Where disagreements arise, calibrations sharpen, samples grow, and the constant remains a quiet answer that continues to work. There is no need to wrestle the origin to the ground before sleep. The world has often asked us to carry a working description, while the deeper explanation takes its time to emerge. We can do that here. A uniform energy with negative pressure acts on the largest scales. The expansion accelerates. Bound systems persist. Distant sources fade from the ledger over long epochs. The near remains near. These are facts stated without urgency. Acceptance is a scientific act when the data are steady and the story stays coherent. Let that steadiness be enough. And if one image must linger, let it be the even film on a winter pane that softens what lies beyond without choosing what to veil. The glass holds, the view changes, the room stays warm. That is how the void's pressure works present everywhere, choosing nothing in particular, reshaping clarity in a way that can be measured and trusted while you rest. Wherever you point a sensitive receiver, the same faint microwave brightness returns with a spectrum that nearly matches an ideal warm body. Its temperature, a bit under 3 degrees above absolute zero, speaks of a time when the universe was hot, dense, and tightly coupled. In that early era, photons and charged particles bounced and pulled against each other, supporting waves that rang through the plasma. As the cosmos cooled and neutral atoms formed, the scattering dropped away. Photons decoupled and began traveling largely unimpeded. We see those survivors today as a uniform glow dotted with tiny temperature variations, each a memory of a ripple frozen when matter and radiation parted. Precision maps from space have charted the pattern of those variations across the whole sky. The power at each angular scale rises and falls in a distinctive sequence. Peaks trace compressions. Troughs trace rarefactions from the acoustic waves that ran through the pre-decoupling plasma. The positions and relative heights depend on the amount of normal matter, the share of dark matter, and the overall geometry. Fits to those data find that, on average, large-scale curvature is small enough that parallel trajectories remain parallel across cosmic distances when averaged. The same fits set the relative proportions of matter and the smooth term that accelerates, expansion, tying the background to later histories. Polarization adds another layer. When photons last scattered, the quadrupole pattern of local radiation left a preferred orientation in their electric fields. That imprint, measured across the sky, bears a delicate fingerprint of the last scattering surface. It also carries traces of later events, such as the epoch when the first stars ionized their surroundings again. By measuring both temperature and polarization, analysts disentangle contributions that would overlap if either were used alone, shrinking uncertainties and exposing subtle features that help refine models. This ancient light calibrates the yardsticks we use today. The dominant acoustic peak encodes a characteristic physical length, the scale of the largest ripples that had time to complete a half oscillation before decoupling. As structure grew, that length left an echo in the way galaxies cluster, a slight preference for pairs to sit at that separation. Surveyors measure the angle that separation spans at different depths and translate it into distances. Because the physical length is known from the background's fit, the comparison anchors the expansion history without relying on how bright things are. It is a ruler rather than a candle. and it agrees with candles when both are used responsibly. Isotropy, the near sameness in all directions, comes with tiny departures that are just large enough to seed everything later. The spectrum of those initial bumps, measured by the background, fits a simple, nearly scale-free pattern with a slight tilt that matches expectations from early rapid expansion models. Those models predicted not just the broad smoothness, but the distribution of fluctuations that would later grow under gravity into filaments and voids. The background's measured pattern thus bridges the youngest view we have to the present web, making the two parts of the story stand together. The background is also lensed by the structures that formed after decoupling. As photons pass galaxies and clusters, their paths shift slightly, distorting the pattern in a way that can be teased out with statistical tools. Reconstructing that lensing field yields a map of integrated mass along lines of sight at intermediate epochs. It is a second way the ancient light contributes to present measurements, giving a census of mass that does not depend on how that mass glows. Combining primary anisotropies with the lensing signal improves constraints on the sum of neutrino masses and on parameters that shape structures' growth. Foregrounds complicate the view, but do not obscure it. Our own galaxy's dust glows and polarizes. Nearby sources add spots and stripes. Experiments deal with them by mapping in many frequencies, modeling emissions with care, and checking solutions by comparing independent patches and instruments. After subtraction and cross-correlation, the leftover pattern is the same wherever we look, as if a seashell held a steady hum that remembers a shoreline we cannot see. The tone is not created by the shell, it is revealed by it. The microwave sky is that kind of memory, honest and soft. The temperature of the background itself cools with expansion. If you could have measured it when the universe was half its present size, it would have been roughly twice as warm. Spectral lines observed in gas at known depths carry imprints of that warmth, and those measurements align with the simple rule that temperature scales inversely with the size factor. That alignment ties a basic thermodynamic expectation to astronomical evidence, turning an idea about redshifted photons into numbers that pass checks far from our local neighborhood. Small departures from perfect blackbody shape are absent to high precision. That absence constrains violent processes that might otherwise have injected energy after decoupling. It tells us that the cosmic thermal history, as far as radiation is concerned, was largely undisturbed after the initial events that set the whole in motion, where distortions might arise in shocks, in decays, in exotic transitions. Upper limits corral speculations into ranges that do not spoil the measured smoothness. Calm where calm is predicted is itself a result. One might worry that such an ancient message would blur beyond use, but the clarity remains. The sound horizon is measurable. The tilt is real. The polarization reveals a clean surface and a gentle reionization. The lensing pattern checks the mass web we map in galaxies. The temperature's value matches what we infer from the distribution of hydrogen at great distances. Among many moving parts, the background stands still in its meaning, a benchmark against which other readings can be set. In human feeling, this afterglow offers a sense of continuity. The same photons that left when atoms first found each other arrive at a dish and become a signal we record. They crossed a changing universe without forgetting where they came from. That steadiness invites trust. You can rest knowing that the past leaves traces gentle enough to observe and strong enough to lean on. The sky hums with an old story, and the measurements tell it with care. Some theories suggest that the three spatial directions we move through might not be the entire set. Extra dimensions could exist, compactified so tightly that everyday energies cannot enter them. If such directions are real, they would change gravity's behavior subtly at short distances, and leave faint marks in the debris of high-energy collisions. Frameworks built on tiny vibrating entities often require 10 or 11 coordinates for their mathematics to close neatly. In those settings, familiar particles arise as different modes of vibration, and the geometry of the hidden directions influences which modes are allowed and how strongly they interact. Experiments ask the world whether these hints correspond to facts. Precision tests of gravity bring small objects close together and measure the tiny attraction between them with torsion balances and micro-cantilevers. If gravity leaked into unseen directions at a certain scale, the inverse square law would tilt away from its usual slope. Measurements down to fractions of a millimeter continue to agree with the familiar rule within tight bounds. Colliders accelerate protons to high energies and watch for events in which the visible debris fails to balance momentum, as if a particle had slipped into a direction detectors cannot access. The patterns largely match known processes. Constraints tighten and theories adjust, not because the idea is wrong, but because the world speaks clearly about the scales it allows to be tested. Astrophysics sets limits from another angle. Stars that cool too quickly would reveal new channels for energy loss if extra directions admitted light or gravity in unexpected ways. Dense remnants would collapse differently if gravity strengthened at short scale. Observations of supernovae, white dwarfs, and black hole mergers leave little room for dramatic changes in how gravity behaves inside those domains. The absence of anomalies becomes a guide. Each bound excludes a patch of parameter space and shapes what model builders try next. The appeal of extra dimensions is not only tidy mathematics, though that tidiness is real. They offer potential unification by placing forces that look different into a shared architecture when seen from a higher dimensional view. Gravity may appear weak compared with electromagnetism, because some of its field lines spread through more directions than the others can access, diluting its apparent strength in the three we inhabit. Small curled spaces can also generate families of particles by how paths wrap and interfere. These are careful possibilities, explored with respect for data and with predictions that can be checked step by step. Laboratories keep sharpening the search. Mechanical sensors cooled close to their thermal limits weigh the attraction between patterned masses while suppressing electric and magnetic nuisances. Atomic interferometers time free-falling clouds along different paths to detect minute potential changes at short ranges. Surface probes bring metallized tips close to test masses while measuring forces with sub-piconewton sensitivity. Each method attacks different systematic errors. Each result is compared with models that include backgrounds and noise. Together, they extend the reach of our questions by small, reliable increments. High-energy experiments look for complementary signs. If extra directions exist with sizes just beyond present constraints, collisions could produce heavy excitations that resemble copies of familiar particles with slightly higher masses, or they could make a graviton vanish into the hidden volume, leaving an imbalance in the visible spray. Analyses group events by topology and energy, then compare counts to expectations from known processes. When small excesses appear, teams add data, refine calibrations, and ask the same question again. Most hints fade under scrutiny. A few survive long enough to shape new runs and trigger fresh designs. That rhythm propose, test, refine, repeat, keeps curiosity awake without mistaking wish for result. Theoretical work connects these searches to broader goals. Models that include warped extra dimensions can generate large differences in observed energy scales without fine-tuning. Others use the shape of the compact directions to organize families of particles and their couplings, turning complicated lists into geometric datasets. Even where direct evidence is absent, These constructions influence how people think about unification and about the origin of constants in the equations that describe our world. The influence is conceptual, yet it flows back into experiments by setting targets worth reaching and behaviors worth excluding. A simple picture can help without promising more than it should. Hold a fine thread at arm's length, and it looks like a line. Under a microscope, it reveals a circular cross-section, a direction you could not walk with heavy boots but could trace if you were small enough. Hidden directions, if they exist, might be that kind of curvature present, influential, yet inaccessible with ordinary steps. Physics may hold surprises at scales far smaller than we can touch. Our honesty remains. No direct sign has appeared. We tell that truth gently and keep improving the instruments that might one day find a bend in the rule. There is comfort in the way this search proceeds. Non-detections are not failures. They mark where the world remains as expected and clear room for other possibilities to be tested. Limits become knowledge that shapes the next attempt. Precision builds slowly, and each measurement, even one that confirms the usual behavior, shrinks the space where ignorance can hide. That shrinking is progress of a quiet kind, the kind that lets you rest with the knowledge that if hidden directions are real, they are not capricious. They would leave consistent, measurable traces. Until then, the space we move through is enough. Another idea speaks softly and reaches deep. Spacetime might not be the starting point. It could emerge from patterns of quantum information, especially from how strongly parts of a system are correlated. In this view, geometry is a large-scale description of relationships. Where correlations are dense and intricate, space looks continuous and close-knit. Where correlations thin, distance opens. Cut entanglement, and regions that once felt adjacent drift apart in the effective map. In simplified models, counting information across boundaries reproduces familiar gravitational equations, as if curvature were a way of talking about how many links cross from one side to the other. Hints come from black holes. Their entropy, the count of microscopic possibilities, consistent with the same macroscopic shape scales with surface area, not volume. That rule suggests that information content lives on boundaries more than in bulk. Extending the idea yields a principle. Under certain conditions, the physics inside a region can be captured by data on its surface at the right resolution. That correspondence has been realized concretely in theoretical settings where a gravity-filled space is linked exactly to a quantum system without gravity on its boundary. In that dictionary, distances and curves in the interior translate into entanglement and dynamics on the edge. The success is limited to specific shapes and symmetries, yet it demonstrates the possibility that space arises from connections. Calculations sharpen the picture. In those models, the entanglement entropy between a subregion and its complement equals the area of a minimal surface that hangs from the subregion's boundary into the interior. Vary the state, and the minimal surface changes. Vary the surface, and the entropy changes, tying geometry to information with precise formulas. Small perturbations of entanglement lead to linearized gravitational equations in the interior, suggesting that the familiar field relations are the macroscopic shadow of deeper bookkeeping about correlations. The idea does not discard observation. It proposes a reason the observations fit the equations they do. Laboratory systems emulate pieces of this logic. Cold atoms, arranged in optical lattices, can be tuned to produce phases with long-range entanglement. Quantum simulators evolve states whose correlations and excitations can be measured directly, testing how patterns spread and how cutting connections changes effective behavior. Networks built from tensors, designed originally as computational tools, turn out to represent spaces whose geometry reflects how components are wired. Adjust the wiring, and the emergent distances shift. None of these are the universe. All of them are small, controllable arenas where the link between information and shape can be examined without myth. If space emerges from connection, time may be tied to how correlations grow. As subsystems interact, entanglement increases, and a direction appears from past to future aligned with that growth. The arrow, then, is not painted on by hand. It comes from how information spreads and becomes harder to reverse. That picture resonates with the ordinary rise of entropy in closed systems, while adding a microscopic foundation for why clocks can agree on direction even when their rates differ. The logic is tentative and not complete, but it provides a path where quantum rules and gravity meet without contradicting each other. Black holes again serve as guides for puzzles about information. If horizons glow faintly and masses can fade, what happens to the details of what fell in? In an emergent picture, the information is not lost. It is scrambled into correlations among outgoing quanta and the rest, encoded in a way that is locally unreadable but globally consistent. Calculations in toy models show how late-time radiation can retain delicate dependencies on early inputs without violating the smoothness of the horizon in the large-scale description. The details are technical. The theme is simple. When space is a description of connections, destroying information is not an option. It can only hide. This perspective also reframes what a region means. If the degrees of freedom that create geometry sit on a boundary, then volumes are summaries, not fundamentals. Counting bits on a surface becomes more natural than counting points in a bulk. That inversion explains why certain quantities, the entropy of a black hole, the complexity of a state scale, with area or with wiring depth, rather than with volume directly. It explains why doubling the radius squares the capacity for information, not cubes it, whenever horizons set the stage. Skepticism is healthy and present. The exact correspondences we possess work best in spacetimes with negative curvature at the boundary, not in the flat or gently curved spaces we inhabit. Translating results to our world remains an open project. Yet the successes have already changed the questions people ask and the tools they use. Information measures have entered gravity. Geometric intuitions have entered quantum theory. The exchange is already valuable, even if the final bridge remains under construction. A gentle picture can close the thought without overpromising. Imagine a tapestry whose image appears because threads cross and hold. Pull enough threads away, and the picture loses continuity before the cloth does. Perhaps space is that image, and entanglement is the weave. Regions look close, where threads tie tightly, and far where ties are sparse. The idea is companionship more than separation. The world is not pieces glued to a backdrop. It is a relation held together by how constituents share information. You belong within that relation without effort because everything does. That belonging changes nothing about the earlier facts. Light still bends because fabric's design guides it. Waves still pass when masses accelerate. Horizons still mark boundaries between what can return and what cannot. The scale still grows on large spans. The new thought offers a reason those facts might hang together, a possibility that the fabric they share is not a surface draped on nothing, but a pattern woven from what degrees of freedom know about each other. It is an invitation, not a demand, to hold two languages at once, one of fields and distances, one of links and entropy, and to let them hum together while you rest. Between those hums, the night remains steady. Measurements will resume in the morning. Equations will still fit. Threads will still cross. For now, the picture can gently fold and wait, as quiet as a loom standing in a darkened room, the pattern intact, the weave secure, and the air almost still. You have walked softly through a structure that does not need footsteps to be real. SpaceTime carried every example without complaint, from slow clocks in valleys to waves arriving from distant collisions. The facts are small lanterns placed at steady intervals. Each one shines just enough to show the next. Together, they describe a universe that is coherent, measurable, and generous with patterns. Curvature became gravity. Light kept its pace. Time changed in honest ways when motion or depth demanded it. Galaxies moved apart because the metric grew. An afterglow filled the sky with a memory that never fades. The quiet pressure of something uniform guided the late chapters. Ideas about hidden directions and emergent geometry stayed polite, adding possibilities without the noise of certainty. Entropy gives the large story a direction, gently increasing the number of ways the universe can arrange itself. Over long ages, structures fade as energy spreads thin and the night grows simpler. Bound islands endure according to their own strengths. Within such an arc, small lives gain meaning through softer measures, steadiness, care, curiosity that does not disturb the dark. Knowledge becomes a pillow rather than a weight. It supports without insisting and holds shape without needing attention. If wakefulness lingers, let one calm thought remain. The same architecture of space and time that guides planets also guides breaths. Clocks across altitudes disagree by slivers and still live peacefully together. Rays bending near mass show paths that are kinder than straight lines through nothing. Waves arriving in arms of light reveal collisions no eye could see, translating violence into a pattern you can listen to without fear. Everything difficult turns into something gentle when you choose the right scale and the right pace. Close your eyes if they want to close, and keep them open if that feels kinder. Either way, the structure beneath you will not change. It will hold your room, your heartbeat, your next gentle minute, and the hours ahead. Sleep does not need pursuit. It can be allowed like an orbit allowed by gravity, like a beam allowed its curve. Tonight belongs to patience, and patience rests inside the most reliable thing we know. Let it hold you. Good night.